Here's a small but important result about relationship between higher and lower moments. If you've watched my videos on MGFs, you might get the impression that you can just churn out any order of moments using the MGF. This is not actually the case. So if you just read this theorem here, these two lines to yourself, I'll just kind of put in layman's terms. If some moments exist, this result says that the lower order moments also exist. For example, if the second moment exists, then the first moments exist. If the third moments exist, so too do the second and first moments. This result holds for continuous as well as discrete random variables, because in the theorem it doesn't say specifically that it has to be discrete or continuous. Also note, and don't confuse that what it does not say. It does not say that if a low moment exists, then so too do the higher moments. If we use the contrapositive statement to this, it does say, if we think about this, this is of the form if this hypothesis, then this condition holds. So this is saying that if high moments exist, then so too do the lower moments. If we take the contrapositive of that, this says what's also true is that if the low moments do not exist, that implies that the high moments also do not exist. Just written down here, just to recap what moments are, if you've kind of just need a recap on that. I'm going to prove this result, and it's good because we're going to learn a few things. First of all, we are going to look more closely at the definition of an expectation. Secondly, we're going to review the properties of probability function. Okay, for this proof we're going to treat x as continuous, and we can do it for the discrete case using the same method but replacing integrals by summations. Okay guys, first we need to look more closely, revisit the definition of an expectation. Often in introductory stats courses you might just find the definition like this. Suppose x is a continuous random variable, then here's the expected value of x just told, and that's it. However, below all here, it's very important that this condition holds for the existence of this thing, i.e. that you can calculate a value for it. So the definition for an expected value where x is continuous is it's this whenever this integral converges absolutely. What do I mean by that? It means that if I replace this integrand here by the absolute sign, just take the positive of it, then this is going to be finite. So we can write it in technical ways like this, less than infinity, which just means it's finite. Notice since the PDF is non-negative, that means when you take the absolute value of this, it really means you just take an absolute value of x, because x can be anything, could be anything from negative into plus infinity. So this condition is what we call absolute convergence. This converges absolutely. It's a result from real analysis. If you're doing that in college, look out for that result. For the sum, it's just the same, just replace sum here, sum there. Then why we need this condition of absolute convergence is because it tells us that the order that we add things up, if we had an infinite sum, will not affect the answer. Otherwise it would, and then we'll get nonsensical answers. To press home what I mean by absolute convergence, and sticking on the point of an infinite series, so we're looking at a discrete case, look at this equality 0, this, okay, so that is that, that is that. By the way, it can just go on and on because it's an infinite series. Then take away the brackets like this, then just associativity, so that plus that. Well, all of these terms are zeros, that's a 1. 0 equals to 1, you've proved, so it seems. But we all know that this doesn't make sense because this series is not absolutely convergent. So the order that you add things do matter. In this case, we can show that this here does not converge absolutely. In fact, it's divergent. Okay, that was just an aside that will give you a flavor of real analysis. So back to the proof. We're given this information, and now we know that if it exists, it means that this condition holds for it. So I've written it down here. This guy is finite. Using that piece of information, then I have to show that for the lower moments that also exists. In other words, this to the power of k where k is less than or equal to m. So if we're looking at this, we want to this should hold if we replace m by a lower number, an integer value, k is finite. Alright, so that's where we're going to go. We need a strategy, and that's the thing about proofs, ideas. So we want to show that the expected value of x to the k where k is some integer value, right, whole number less than or equal to m, but not below 1, is equal to this guy. By definition, it's over here. Now the next line, what have I done? Well, instead of integrating over the whole of the real line, I've split it into two segments. Alright, so less than or equal to 1, bigger than 1. The question is, why have I done that? Well, somehow I have to get this guy into my expression on the right hand side. At the same time, I know I'm not going to get numerical value on the right hand side because I don't know the form of the PDF, right? So most I can go for, this is when I'm thinking about inequalities. Right, so this guy, let's just draw it over here. Okay, do it in a different, let's do it in a different color. Alright, green. I know some people who are colorblind can't see that. Alright, so let's say this is x, the real line. Okay, this is -1, this is +1. So this says integrate over the region here between -1 and +1 inclusive. That's the left, that's this bit. And then this says integrate outside, so then it's, oops, it doesn't include 1, that's what I'm saying, in blue. So I split the two segments. Alright, and that way I've partitioned this space into two blocks, this and outside it. Now why have I chosen the value 1 instead of some other number? Right, it's because of this. I'm taking powers, right? Some x value to the power of k, where k is an integer. What we know is if x is between -1 and +1, if we look at the absolute value of it, so if it's basically, yeah, we take the absolute value of this guy and it's basically between 0 to 1 inclusive, then if you take a power of it, it's going to become a smaller number because it's a small number. Yeah, you can see that. On the other hand, for x bigger than 1, if I take the power of it, this is now going to be, it's going to increase, isn't it? It's going to be bigger than x. So next line, see how I got my inequality, because I replace this guy by 1 because this can't be, it can only be less than or equal to 1. Being equal to 1 if x takes the value 1, because 1 to the power of 1, 2, 3, 4, 5, whatever, it will be 1. So as soon as I stick a 1 there, this quantity is bigger than or equal to this. Let's look at the second term. Now look, now I managed to get my m in here. Okay, so this guy here, because x is bigger than 1, this guy is going to be bigger than this guy, and so the integral, this guy of the same space, this guy will be bigger than, this will be bigger than or equal to as well. Why do I say equal to there? Because in the question it says that k can be equal to m. Not only less than, it can be equal to m. So it'll be equal in the case that k is m. That's why I have not got a strict inequality, it's bigger than or equal. Being equal, just pushing the point home, if x is equal to 1 and m is and k are the same. Cool, I'm almost there. This is almost the expected value of the absolute value of x to the power of m. It's just I need to integrate it over a larger space, right? So that's what I'm going to do in the next line. Now I'm going to extend this just here to the entire real line. And since I'm integrating over a bigger region, this can't be less than that. So that's why I introduced another inequality. It's because it's not because this is the same as that. It's because this term and this line here is bigger than the second line. Okay, it's not the same as the second line. Likewise, this one now, we extend it over the range of the interval of the integral, and by definition, this is that. the expectation of the absolute value of x to the power of m. And by the hypothesis, this is finite. It's an if statement. That's good because that means now this here is less than or equal to 1 plus this, which we know is finite. So it itself must be finite since the right hand side is so. And because it is absolutely convergent, we've shown the condition of absolute convergent, therefore the expectation exists. Done. Okay, so we can look back at the result now. Small, as I said, but useful result. It's more useful for like more theoretical kind of stuff you do, but in introductory courses you might see also like in Chebyshev's inequality. So there, if you're told that the variance exists, you also know that the mean exists. Right, so that's it. I don't know how many of you see this result in the introductory textbook, but I came across it in the introductory textbook. Larson and what was it? Larson and Larson and something. Anyway. Okay, I just had a look at it. Larson and Marx. Okay, so it's in there. That's a very introductory text. So do you see it? If so, where do you study? I'll be interested to know. All right, cheers, guys.